In this demonstration, we will showcase the 5G Clarity Smart Tourism solution designed to enhance visitor experiences and promote public safety in a museum environment. Our smart tourism application features a humanoid robot and offers two distinct services: human-robot interaction providing visitor-guided services, and video service deployment through a natural language processing interface powered by an intent engine. We demonstrate two goals. One, how the Smart Tourism application, a visitor assistance service, is deployed over the 5G Clarity multi-connectivity framework and fulfilling the service KPIs. And two, how the 5G Clarity intent engine can be used by the museum safety officer as a management enabler to dynamically provision on-demand public safety service. This is the 5G Clarity system architecture. The network elements used in our Smart Tourism application are denoted by red ticks. Also, the locations hosting the RAN and Edge clusters are labelled. 5G Clarity Smart Tourism application can be implemented through the following main devices: a humanoid Pepper robot, fixed wireless cameras, Li-Fi dongle, 360-degree camera, a 5G Clarity multi-connectivity CPE enabled with MPTCP with link aggregation capability, a 5G radio, Wi-Fi 6 and Li-Fi access points. Here is the Smart Tourism app architecture and service KPIs requirements. Each device has its own indicated uplink capacity requirement, resulting in a total uplink requirement of 140 megabits per second. A single wireless access technology would struggle to support this uplink requirement with consistent and reliable connectivity across the entire coverage area of the museum. This demonstration shows the 5G Clarity multi-connectivity framework can provision enough capacity to support this uplink requirement. The fixed wireless cameras are used to detect movements pictured in frames, which helps robots enhance their self-awareness capabilities. The detected movements are converted into a grid map with dots that shows locations of obstacles. This information guides the robot along a path free of obstructions. The size of uplink traffic sent to the server can vary depending on the number of people and movement captured by the fixed wireless cameras. In this section, we present the uplink KPI validation of 5G Clarity multi-connectivity framework in Smart Tourism application. Our intention with the experiment is to benchmark the uplink capacity and investigate the effectiveness of the 5G Clarity multi-connectivity framework in supporting the maximum uplink requirement of 140 megabits per second everywhere within the coverage area. To achieve this, we saturate the channel to simulate a high-demand scenario and test the framework's capability to handle heavy network traffic conditions while providing consistent and reliable uplink throughput. The robot starts from under a Li-Fi access point and within coverage areas of 5G and Wi-Fi 6 signals. From the graph, we see the connection established to Li-Fi, 5G and Wi-Fi 6. As the robot moves from this location, we lose the Li-Fi connection but stay connected to 5G and Wi-Fi 6. This is reflected in the Li-Fi graph and aggregated throughput result, shown in the upper graph, which indicates a drop in signal. As the robot moves, the 360-degree and fixed cameras begin to transmit feeds. Wi-Fi 6 exhibits high data rates with signal fluctuations. Its throughput decreases as the distance from the access point increases. The performance of 5G NR stays consistent throughout the coverage area, maintaining an average throughput of around 100 megabits per second in all sections of the demonstration area. Li-Fi re-establishes connection at the second location, but loses the connection as the robot moves further away. Eventually, Wi-Fi 6 falls below 5G, but the aggregated link is able to still support the uplink requirement with enough capacity for the use case. In this section, we present the validation of public safety service through Intent Engine. In order to deploy feeds from the 360-degree camera to a safety officer's monitoring device, a new VNF needs to be provisioned dynamically to redirect the video stream to the safety officer's device. We see the process of how intent is initiated and how the related network services are provisioned. 1. An intent request is made using natural language from the safety officer's device. 2. The 5G Clarity Intent Engine generates call logs and creates an instance of the network service. 3. In the OSM GUI dashboard, an orange tick confirms that the NS instance has been initialized. 4. The OpenStack GUI dashboard shows the VNFs are instantiated. 5. When the OSM dashboard verifies that the NS instance has passed its instantiation and validation tests, and the ticks turn green to indicate that it is now running. Finally, the requested 360-degree video service is deployed on the safety officer's device through the downlink stream. In this section showcases the human-robot interaction.
Welcome to the 5G Clarity Smart Tourism demonstration, enabling enhanced human-robot interaction, here at the Bristol M. Shedd Museum. At the M. Shedd Museum, you can learn about significant cultural, artistic, historical, scientific, and industrial heritage. If you are happy, I will show you a section of the Bristol People Museum. Would you like to come with me?
Yes, I'd like to.
That's great. Come along and explore with me. Here is an exhibition about human rights and voter education. There are lots of things to see and learn. Why not take a look at how much difference your vote can make as you explore this exhibition? I hope you enjoy your time visiting the M. Shedd Museum. Thank you.
Thank you for watching this demonstration.